Let us learn about the next property of orthogonal matrices. So, if A is an orthogonal matrix, suppose A is an orthogonal matrix, then what will happen? Then we have to show that A transpose is also an orthogonal matrix. Okay. So, transpose of an orthogonal matrix is also orthogonal. That's what we have to prove. Okay. Transpose of an orthogonal matrix is also orthogonal. If A is orthogonal, then A transpose is also orthogonal matrix. Let us prove this. Suppose it is already given to us that A is orthogonal matrix. So A is orthogonal matrix, it is already given to us. So if A is orthogonal, that what will happen? If A is orthogonal, then this condition will hold good. If A is orthogonal matrix, then this condition will hold good, that A transpose will be equal to identity matrix, and that will be equal to A transpose A. Okay, A transpose will be equal to identity matrix, and that will be equal to A transpose A. This is from the definition of orthogonal matrix. This is from where? This is from the definition of orthogonal matrices. From definition, which we have already learned 2 years ago, 2 lectures ago. Okay, 2 lectures ago we have learned this particular property of orthogonal matrix, that A transpose is equal to I and A transpose A is equal to I, and all of them are equal. Okay. Now in this equation, take transpose of this equation. So this complete entity's transpose will be equal to this entity's transpose, and that will be equal to this entity's transpose. So take transpose on all the sides. So A transpose transpose. So the first term is A transpose. So its transpose will be A transpose transpose. The second term is identity matrix. So identity matrix transpose. So identity matrix transpose. And the third term is A transpose A. Third term is A transpose A. So its transpose will be A transpose A transpose. Okay. Now we already know this particular property, that which property do we know? We know this property that AB transpose is equal to what? It is equal to B transpose A transpose. This property we already know. Okay. So by using this property, what can we do? By using this particular property over here, this A transpose will come in the front, because in the place of B there is A transpose. The difference between this and this is that in the place of B, A transpose is over here. So by applying this property, this will open up as A transpose, and this A will go over here in the last. This first A will go in the last, and it will become A transpose. This A transpose, which is second term, will become the first term, and A transpose will happen. Okay. Now transpose of an identity matrix is identity matrix itself. Transpose of an identity matrix is identity matrix itself. So it is as it is. Now have a look over here. Similarly, this property you will apply here as well. So in the place of A there is A transpose, in the place of B there is A. So A transpose will become the second term, its transpose will be taken, and the second term will become the first term, and its transpose will be taken. Okay, by using this property. Now do not go in the next step. What I am saying is that A transpose we all know is equal to A transpose is equal to A, we know this. And A transpose, that is transpose taken 2 times, will be equal to the matrix itself. That we know, but no need to go on that step. Okay, no need to go over that step by simplifying A transpose is equal to A transpose is equal to A. No need to do like that, because if you do like that, you will reach here itself. You will once again reach here itself. So let it remain in this form only. And compare by the definition of orthogonal matrices. Compare this expression by the definition of orthogonal matrices. So after you compare this expression with definition of orthogonal matrices, you will realize that A transpose is orthogonal matrix. Okay, this expression, if you compare with the definition of orthogonal matrices, okay, in the definition of orthogonal matrices, if you replace A with A transpose, in the definition of orthogonal matrices, you will get this particular thing. Okay, so A transpose is orthogonal. This expression implies that A transpose is orthogonal matrix by definition of orthogonal matrices. So we started with A is orthogonal. And we reached over A transpose is orthogonal. Okay. So it means that the transpose of an orthogonal matrix is also an orthogonal matrix. It simply implies, what does it imply? It simply implies that transpose of an orthogonal matrix is also orthogonal matrix. This is what is the conclusion which we can draw from here. Because we started with an orthogonal matrix, we reached at the transpose of orthogonal matrix, and that transpose also came out to be equal to the orthogonal matrix itself. So we can say that the transpose of an orthogonal matrix is also an orthogonal matrix. Okay.